Hello ladies and gentlemen, in this video we're going to discuss Android Runtime, or in short, just art. To understand the role of art in Android ecosystem, let's start with the build process. So we take the source code that we write in the form of Java, Kotlin or XML files and compile them into so-called class files. These files contain so-called bytecode, and then further we convert the class files into DEX files using a tool called Dexer. Now these DEX files are then packaged into APK files, which can be distributed to the users. As you might know, APK contains more than just DEX files, but for the sake of our discussion today in the context of Android Runtime, it's sufficient to say that APKs contain DEX files. And then of course we distribute our APKs to the users. And now let's understand what happens during installation and execution process. So first of all, DEX files are extracted back from the APK. And the APK is really just a zip archive, and therefore it's unarchived and DEX files are taken out of that. And then DEX files are fed into this special component which we call Android Runtime. So the inputs into Android Runtime are DEX files. What the outputs are? Well, Android Runtime converts DEX files, bytecode basically, into so-called machine code. And machine code is called machine code because it can be understood by a machine. And the machine, in this case, is the CPU on your user's devices. So the role of Android Runtime art is to take in DEX files and convert the bytecode that they contain into machine executable code. Now, art is exceptionally complex component and we can ask lots of questions about it. For example, what kind of optimizations does ARM perform? What kind of output does it produce? Are these files? Yes, there are files, but in some cases art puts the machine code into in-memory cache, and it's very interesting to discuss, but frankly, nothing of that is very relevant for a regular Android developer because you don't interact with art in most cases. You just assume that it will be there and will do its magic. So what questions do we ask in this video then? Well, I find this question very interesting. Why don't we just compile our source code directly into machine executable code? Why do we need to go through all these intermediate representations, class files, DEX files, and then having Android Runtime translate DEX into machine executable code? Why can't we just, during build process, compile our source code directly into machine executable code? And if you've ever worked with NDK, Native Development Kit for Android, that allows you to write C and C++ code in the context of your Android application, then you know that that code will be compiled directly into machine executable code. So why do we need to compile Java and Kotlin code into all these intermediate representations? That's a non-trivial question. And the answer to this question actually starts with Java's premise back in the 90s to write once, run anywhere. That was kind of the marketing slogan for Java, and let's understand where it comes from. Consider CPUs, central processing units. There are different types of CPUs, and they differ by kind of, the type of the language that they understand. It's called instruction set architecture. Never mind, just a language that the CPU speaks. And of course, if you want CPU to do anything for you, you need to speak its native language. Now, in this case, let's discuss two types of CPUs. One of x86, which is from Intel, and another one is ARM architecture, which is from ARM. So let's suppose we want to write C++ application. What do we do then? Well, we take our C++ files, source code, and feed it into build process. And the output of this very long and complex build process will be two files. One will contain machine code for x86 architecture, and another one will contain machine code for ARM architecture. In other words, if we want to execute our C++ source code on multiple processors architectures, then we need to compile this source code to each individual architecture separately. It's a really complex environment, really complex toolchain, and C++ developers deal with that. And once they resolve all these problems, they will have these executable files that they then distribute to the users, which can execute them directly on their CPUs. So that's what happens in the C++ universe. Now let's understand what happens with your Java source code. So first of all, Java source code is also fed into the build process, but the output of this process are class files, which contain bytecode. So bytecode is an intermediate representation. Intermediate representation is a term that comes from the compiler's universe. It's basically something that we generate and then we kind of convert it to another representation later. These files, class files, are what we distribute to our users. And of course, we want to distribute the same class file to both architectures. However, as we said, these processors speak different languages, and actually neither of them understands the language encapsulated inside the bytecode that we distribute as class files. So we need some company to translate the bytecode from class files into native languages for specific architectures. And this company is called JVM, Java Virtual Machine. Java Virtual Machine takes in bytecode and produces machine code that specific processor can then execute. And of course, we immediately see that the precondition for executing Java compiled bytecode on a specific processor is that there is an installed Java virtual machine there. And therefore, before you can execute Java, you need to have JVM installed. So that's kind of a different approach from C++ universe, where you distribute machine executable code that you can directly run on these CPUs. All right, so these are the different approaches between C++ and Java, but why do we need them? Why Java decided to go another road? And to understand the difference in the kind of the use cases for these two approaches, let's consider the situation when we have a new CPU architecture that we want to support. So let's say we want to execute our C++ application on another CPU architecture. What we need to do then? Well, we need to recompile our source code from scratch for that specific CPU architecture, just like we did for these two architectures. And therefore, if there's ever a new CPU architecture that emerges and we want to support it, we will need to recompile our application. But of course, there are tens of thousands, maybe different applications. So all of them will need to be recompiled, rebuilt in order to support this new architecture. And the people who use this new architecture will need to wait for all these applications to be recompiled, and some of them will never be built for that architecture, so they lose the ability to execute those apps there. So that's what happens if a new CPU architecture emerges and you want to support it using your C++ code. In Java world, it's a little bit different. In Java world, you don't need to do anything. You can use exactly the same class files like before, and just the moment someone creates a new implementation of a Java virtual machine that supports the new processor architecture, immediately you can execute your application on that architecture. Well, as long as, of course, your users install that Java virtual machine. And the question now becomes who kind of implements those Java virtual machines, and the answer is that big companies do. So you kind of assume that someone will implement a new JVM if a new processor architecture emerges and becomes popular, and the moment it happens, boom, the entire ecosystem of all the existing Java apps can take advantage of that new JVM and then be executed on this new target architecture. So that's the benefit of Java. That's the promise of write once, run anywhere. At this point, I just like to emphasize that neither of these approaches is better than the other. These are just different approaches. They have different trade-offs associated with them. And in some situations, a C++ approach is more convenient, and in other situations, Java approach is more convenient. So different sets of trade-offs. And that's what happens with Java. And then when Google worked on Android, when they developed Android, they decided to use Java. And therefore, they kind of adopted the entire flow of Java ecosystem. And therefore, they adopted this notion of having some kind of a virtual machine to interpret the bytecode. However, they didn't take it as is. They modified the flow a little bit to accommodate additional constraints. And one of the most important constraints that they wanted to accommodate was devices with very little RAM memory. So instead of distributing class files, they implemented a conversion, additional conversion into DEX files, which are more optimized for low RAM devices. And in addition, they did not use Java Virtual Machine, and they did not implement their own implementation, certified implementation of Java Virtual Machine, but instead they implemented their own virtual machine. They called it Dalvik, which at a later point in time was replaced by Android Runtime, ART. So today we use ART, before that we used Dalvik, and Dalvik and ART are just basically customized versions of Java Virtual Machine. Alright, this explains what happened. Google decided to use Java, so they inherited all this kind of architecture from the Java world. But it doesn't explain why Google decided to use Java specifically. Weren't there other alternatives that they could use? Well, surely they were. But Let's see this email from the year 2010 from Tim Lindholm, who was one of the lead developers on the Android projects, to Andy Rubin, who is considered to be kind of the father of Android. I highly recommend that you pause the video right now and read the entire email. It's very interesting and insightful, but what I want to emphasize are these two lines from this email. So what we've actually been asked to do, Tim writes, by Larry and Sergey, founders of Google of course, is to investigate what technical alternatives exist to Java for Android and Chrome. We've been over a bunch of these and think they all suck. So Google actually tried to find other ecosystems, other alternatives to Java for Android, but eventually they concluded that they all suck. It's Tim's words, not mine, and therefore they decided to adopt Java. So Art, Android Runtime, is a downstream artifact of Google's decision to take advantage of the existing Java ecosystem when they developed Android. So they decided to use Java because it was the best solution for Android, and Java comes with the assumption that the bytecode will be converted by the JVM into machine code, so Google kind of inherited all of that. And today we have Art, which is a modified version of Java virtual machine specifically for Android. Of course, we discussed Java, but Kotlin, which is the standard language for Android today, is also a JVM language. And therefore, Kotlin, just like Java, is converted into the bytecode and then into DEX files, which are then fed into the Android runtime. And therefore, even though the entire ecosystem transitions to Kotlin right now, Android Runtime retains its position and relevance going forward. And by the way, you might have heard that at some point Oracle sued Google over its usage of Java in Android. Well, that's the reason. Google decided to adopt Java for Android, but instead of licensing Java from, well, Sun back then and then Oracle, they just decided to implement their own Java virtual machine, Dalvik, and then Art, Android Runtime. And Oracle didn't like that, so they sued Google, and there were multiple years of these legal battles and millions of dollars were spent on lawyers probably, and eventually the Supreme Court of the United States just decided that Google's use of Java in Android world constitutes so-called fair use, and therefore Oracle doesn't have any claim for damages in this context. Okay, so that's Android Runtime in a nutshell, and I hope that you enjoyed this video. I will see you in the next one. Goodbye.